Okay, this is chapter 9. On the recorded video, we already explained the section 1 of chapter 9, definition of power series. And today we will go for how we can find the power series for any function and how we can find the Maclaurin theorem, how we can apply the Maclaurin theorem. So what we explained in part 1, the power series, we said that the power series is any series that have a polynomial formula. This formula is the power series. This is the formula of a power series centered at 0. The center of this power series is at 0. And if you notice here, it is similar to the polynomial series. C0, C1, C2, C3, Ck, all are constant. All are real numbers. So what the benefit, what the advantage of writing, of having a power series? You can see that the power series can easily integrated. We can integrate it easily. And also the derivative also can be obtained easily because all these terms can be easily integrated and easily also differentiated. So here we need to know first when the power series is converge. What are the interval of convergence of power series? And this is what the part 1 of chapter 9. We explain how we can find the interval of convergence of power series. So power series, to know the interval of convergence, we have to apply either a ratio test or a root test. If you apply the ratio test, usually we apply ratio test. For example, we have this power series, x to the power n, which means that this is a power series. When you see x to the power n, this means this is a power series, alternating power series. So apply the ratio test. By applying the ratio test, we have the term n plus 1 over the term of n, 8n plus 1 over a of an. So taking the limit, we explain all this on the video recorded before. So we have the limit absolute value of x according to the ratio test. To be convergent, this value or this limit should be less than 1 because less than 1 means converge. So when absolute value of x less than 1, which means that x lies between -1 and 1, and this is your interval of convergence. The series is converged from -1 until 1. Outside this interval, the series is diverged. The series is diverged. This interval from -1 and 1, the center is 0 here, and the radius of convergence is 1. The radius of convergence is equal to 1. The interval from -1 until 1. So this is the, at any point between -1 and 1, the series converge. Outside, the series is diverge. But we still have a problem at the boundary point. When x equal to -1 and x equal to 1. We don't know if it is converge or diverge. So you have to check. At the boundary, you have to check separately. You have to check at x equal to -1 if the series is converge or diverge. And then you have to check also at x equal to 1 if the series converge or diverge. So we substitute here x by -1. So we have this series. We replace x by -1. We have a new series. When we write the terms of this series, we found this series is equal to -1 over n. -1 over n is diverge harmonic series. Is a diverge harmonic series. So this means that at x equal -1, the series diverge. The series diverge, so it is not included on the interval of convergence. Now we have to check at x equal to 1. At x equal to 1, we replace x, we go for the original series, we replace x by 1. We replace x by 1. So we have a new series, this one, when we replace x by 1. This is alternating series. This is alternating series, so we have to apply alternating test. Alternating test, decreasing, limit equal to 0, so converge alternating series. So 1 already included in the interval of convergence. So your interval of convergence from -1 and 1, including the point 1, but not the point -1. Not the point -1. All this we already explained in detail, so please all of you see the video of chapter 9. This is another example we already explained. We apply a ratio test again to find the interval of convergence. But here we have limit equal to 0. Here we limit equal to 0. So the interval of convergence is all the real numbers. All the real numbers, the series always converge. Always converge. There is no diverge for this series. Divergence point for this series. And this is another example. We already apply the ratio test again. Then we have absolute value of x squared less than 1, which means that the absolute value of x less than 1, the square root of 1, which is 1. So x again between -1 and 1. So here your interval is from -1 and 1, centered at 0. Radius of convergence equal 1. Here the radius of convergence equal 1. So we need to center at 0, so we need to check the boundary point. This is their interval. You have to check the boundary point. Any point greater than 1 or less than -1, the series diverge. Between -1 and 1, the series converge. But -1 and 1, the point of the boundary of the interval, you have to check separately. So at x -1, you need to substitute here x by -1. So x by -1, we have this alternating series, and by applying alternating test, the series converge. At x equal 1, when substitute x by 1, we have another alternating series, also converge. So your interval this time from -1 and 1, and including the point -1 and 1. And this is also the fourth example we explained on the part 1. Which is, but here the power series centered at 1, not at 0. The previous example, the series, we have x to the power n, which means that the series centered at 0. But here your interval will be centered at 1, because x minus 1 equal to 0, which means that x equal to 1. X equal to 1. But the same process, you have to apply ratio test first. When you apply ratio test, you less than 1. So you need to find the interval, or maybe the, okay, on the video we'll find the complete solution. It will be from -1 and 1, and the interval from 0 to, okay, I will upload the solution again. There's a problem here, but on the video you will find everything complete. Okay, today we will go for power series for a function. Power series of a function. How we can write the power series for a function. Why we need to write any function as a power series. Why we need to write any function as a power series. As we said before, that when I write the function as a power series, then I can easily find the integration for the function and the derivative of the function with respect to x. Because we can easily integrate these terms and we can easily differentiate this term. For example, if I go to the function 1 over 1 minus x, this function can be written as this series 1 plus x squared plus x cubed and so on. Also, the function 1 over 1 plus x can be written as a power series 1 plus minus x plus x squared minus x cubed and so on. So when I write 1 over 1 minus x as this one, instead of find the integration of the function directly, you can integrate these terms. Also here, instead of integrating the function 1 over 1 over x, 1 over 1 plus x, you can integrate this one, which is more easier, So the question is, how we can write this function as a power sum. How we can write 1 over 1 minus x as this function. How we can write 1 over 1 plus x as 1 minus x plus x squared and so on. So this is the theorem why we need to write the function as a polynomial, because it is easily, when we need to find the derivative, you only find the derivative for these terms. The derivative of the constant is 0. The derivative of c1x is c1. The derivative of c2x squared is 2c2x squared. The derivative of c3x cubed is 3c3x squared, and so on. Integration same. Integrate each part. C0 is C0 x. C1x is C1x squared over 2. C2x squared, which is C2x cubed over 3, and so on. Well, so now we need to know how to write any function. If I give you any function, how you can write it as a Maclaurin, as a polynomial or a power series. So we need to apply a Maclaurin theorem. Maclaurin theorem states that if you have any function, so the polynomial or the power series of your function or the polynomial series of your function can be written as f at 0 plus the derivative of f at 0 multiplied by x plus the second derivative of f at 0 over 2 factorial x squared plus generally nth term is the derivative n plus 1 at 0 over n plus 1 factorial x n plus 1 x to the power n plus 1. This is the theory that we will apply to find the power series for any function. This one. We call it Maclaurin theorem because we find this function when at 0 point. 0 point means that Maclaurin theorem. Maclaurin always at 0. Okay, now here we go for example. I have this function 1 over 1 plus x. I need to find the polynomial or the power series for this function, and we will prove it is equal to this one. 1 plus x squared plus x cubed, and so on. 1 over 1 plus x is 1 minus x plus x squared plus x cubed. Okay, we need to find it. So I have the function, your function f of x is 1 over 1 plus x. And we need to find the power series or the Maclaurin series. Maclaurin series or the power series. First, we need to, according to this theory here, we need to find f0. We need to find f of 0. F of 0. So here f of 0 is equal to 1. When you substitute x equal to 0, f of 0 equal 1. Now, second term is f prime of 0 times x. F prime of 0 times x. This is the second term. So you need to find the derivative of f of x. We will find the derivative for this function. The derivative here, 1 plus x squared. 1 plus x times the derivative of 1, which is 0, minus 1 over 1 times the derivative 1 plus x. 1 plus x, the derivative of 1 plus x is 1. So minus 1 times 1, which is minus 1. So this is the derivative of f of x. Now, f prime of 0 is minus 1. Substitute x equal to 0, you have f prime of 0 is equal to minus 1. Okay, third term, we have to find the second derivative of the function f. We have to find the f at 0. So we need to differentiate another time. So again, 1 plus x to the power 4. So you have 1. Now 1 plus x squared times the derivative of minus 1, which is 0. Minus minus, which is 1. 1 times 2, the derivative of 1 plus x squared, which is 2, 1 plus x. So this one becomes 2, 1 plus x to the power 3. 1 plus x to the power 3. We need to find the value at 0. F double prime of 0 is equal. Substitute x by 0, which is 2. And you can also find, the third term, you can differentiate x another time. If you differentiate f of x, another time, you have this one. You have to find the derivative of this function. The derivative is 1 plus x to the power 6. 1 plus x cubed, the derivative of 2 is 0, so cancel. Minus 2, 3, 1 plus x to the power 2. And this one is equal to minus 6 over 1 plus x to the power 4. So now calculate f triple prime of 0, which is, substitute x by 0 here, so minus 6. Now we need to write the Maclaurin series. According to this theory. So f of x here is 1 over 1 plus x. So f of x which is 1 over 1 plus x is equal to f0. First term is f0. F of 0 is 1. Plus. Second term is f prime of 0 times x. So f prime of 0, which is minus 1 times x. Plus. Third term is the second derivative of f at 0 over 2 factorial x squared. So here the second derivative of f at 0, which is 2 over 2 factorial x squared. Plus. Okay, f triple prime of 0 now, which is minus 6 over 3 factorial x cubed, and so on. You can continue. Okay, now we write this one. So you have 1 plus x equal to 1. First term is 1. Minus 1 times x, which is minus x. 2 over 2 factorial is 1, because 2 factorial is equal to. So 2 over 2 is 1. So plus x squared. Minus 6 over 3 factorial. 3 factorial equal to 6. So minus 6 over 6 is minus 1. So minus x cubed answer. So this is the polynomial or Maclaurin series for the function 1 over 1 plus x. How we get it again? This is your function. You need to apply the theorem. You need to apply the theorem to find the Maclaurin series. So this is the function. First, Maclaurin means that x should be equal to 0. All the terms will be calculated at x equals 0. So x, first, f at 0, f of 0 is equal, substitute x by 0 here. So 1 over 1, which is 1. Now, second term, we have to calculate the derivative of f. So go for f of x, find the derivative, which is minus 1 over 1 plus x squared. Now, calculate this one at 0. Substitute x by 0. So f derivative of 0 is equal to minus 1. Now, second derivative of f at x. You need to calculate to find the third term. So differentiate this function again. You have the derivative equal 2 over 1 plus x cubed. Calculate it at 0, so it equal 2. Then go and find the derivative for this function again, the third derivative. So here differentiate this one, 2 over 1 plus x cubed. So 1 plus x to the power 6. 1 plus x cubed multiplied by the derivative of 2, which is 0, minus 2. The derivative of 1 plus x cubed is 3, 1 plus x squared. So minus 6 over 1 plus x to the power 4. At 0 is equal to minus 6. Enough here. No need to continue to find more terms. First 4 terms is enough. So first term is 1, f0. Second term is f prime of 0, which is minus 1 times x, plus second prime of 0, second prime of f at 0, which is equal to 2 over 2 factorial x squared. And then third one, minus 6 over 3 factorial x cubed. We apply this one, this theory. We apply this theory, this term. Now this is your series, 1 minus x plus x squared minus x cubed. If you have any question, you can ask in chat or you can open the mic. If anything is not clear, you can ask. Okay, now we need to use this one. We need to use this one. Okay. We need to use this one to find the function 1 over 1 minus x. We already find the function, that's the Maclaurin series of the function 1 over 1 plus x. Now I need to find the function or the Maclaurin series for the function 1 over 1 minus x. 1 over 1 minus x. How we can find the function 1 over 1 minus x? Should we go to repeat all the steps again or how? I need to find 1 over 1 minus x. Should we repeat all the terms or we can use this result? What do you think? Can we use this result to find the function 1 over 1 minus x, or we have to repeat all the terms? What do you think? We have to repeat, or we can use this one? What do you think? Yes, can use the result. Yeah, can use the result because no need, you can go for to repeat all the previous steps, but easier for you to use this result because this one is equal to 1 over 1 plus minus x. 1 plus minus x, which means that I will replace each x by minus x. I will replace each x by minus x. So 1 minus, instead of x, write minus x, plus minus x squared minus x cubed, plus and so on. Go here and replace each x by minus x. Replace each x by minus x. So you will get this one is equal to 1 plus x minus x squared, still x squared. Okay. Minus x cubed is minus x cubed, and we have another minus here, so plus x cubed, and so on. So this is the Maclaurin series of the function 1 over 1 minus x. No need to repeat all the steps again for the function. If you repeat, you will get the same result. But easier to use this one because this is same series, but only x is replaced by minus x. X is replaced by minus x. Okay, now we go for another example. We need to find the Maclaurin series for the function e to the power x. We need to find the Maclaurin series for the function e to the power x. So we will apply the same step again. Maclaurin series means x equal to 0. X equal to 0. So this is your function f of x is equal e to the power x. At 0, f of 0, e to the power 0, which is 1, which is equal to 1. Now, f prime of x. The derivative of e to the power x, same. The derivative, same. So the derivative at 0 is still e to the power 0, which is 1. Okay, the second derivative of x, which is e to the power x, at 0. Maclaurin series, you need to calculate all these values at 0. So the second derivative of f of at 0 is equal to e 0, which is 1. Still we get 1. So if you continue, we still get 1. So your function, Maclaurin series, is equal to f of x, which is e of x here, e to the power x, is equal to first term f0. F of 0 is 1. F of 0 is 1. Plus second term should be the derivative of f at 0, which is 1 also, times x, plus second derivative of f at 0, which is also 1, times x squared over 2 factorial, plus 1 over x times x cubed over 3 factorial, and so on. If you continue, you still get 1. So here this series is 1. This is the Maclaurin series of the function of the exponential function e to the power x, plus x squared over 2 factorial, plus x cubed over 3 factorial, and so on. So this one is equal to x to the power n over n factorial when n started from 0 to infinity. So we already proved this one. Exponential function is equal to the summation from x to the power n over n factorial from n equals 0 to infinity. We apply Maclaurin theorem. Maclaurin theorem calculate the value of the function at x equals 0 to have the first term here, which is equal to 1. Then differentiate the function and find the value of the derivative at x equal to 0. We also get 1. Then go and differentiate the function again to get the second derivative. We still have exponential function at 0, still have 1. So your Maclaurin series is first term is the value of f at 0 plus the value of derivative at 0 times x plus the value of the second derivative of 0 times x squared over 2 factorial plus the value of third derivative of 0 over 3 factorial times x cubed, and so on. So this is the Maclaurin series. If anything is not clear, you can ask on the chat. How we can get this one? Just take the function, calculate the function at 0, calculate the derivative at 0, calculate the second derivative at 0, and so on. Now we need to use the Maclaurin series, this one. This is the part A for the question. Part B, we need to find the value of E. We need to find the value of E. If you go in your calculator, the value of E is equal to 0.71828. Maybe this is the value that you get from calculator. But now I will try to calculate E by using Maclaurin series. Maclaurin series. He asks you to use n equal to 9, which means that you need to calculate on the first 9 terms. The first 9 terms. So this is your Maclaurin series. F of x, E of x is equal to e to the power x is equal to 1 plus, from here, 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial and until x to the power 9 over 9 factorial over 9 factorial. So we need to calculate this one. Need to calculate. Now E, when I need to find the value of E, which means that x equal to 1. X equal to 1. To get E should be x equal to 1. So 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial until you reach 1 over 9 factorial, because the question asks us to use 9 terms. That is n equal to 9. So you stop at n equal 9. You have to stop at n equal 9. Now calculate these terms by calculator. You will find E, or the summation, is equal to 2.718281556. Now if you need to compare the calculator result directly and your summation here by using the Maclaurin series, you have the first 6 decimals are same. First 6 decimals are same. 718281. Here, 718281. The error started from the 7th decimal. The error started from the 7th, which means that we have a high accuracy of the result. High accuracy of the result. So again, how we find E? This is first we calculate because we need to know the accuracy. So this is the this value we obtain it by using calculator, because I will use it to compare. Now I need to find it using Maclaurin series, using this Maclaurin series. Maclaurin series for the function e to the power x states that e to the power x equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial until x to the power 9 over 9 factorial. We stop at n equal 9. I need to calculate E, which means x equal to 1. X equal to 1. So x equal to 1, you have the value of E. 1 plus x, replace x by 1, x squared by 1 over 2 factorial, x cubed, which is 1 also, over 3 factorial, until 1 over 9 factorial. If you find the summation here, if you evaluate the summation, you get this result. Now, if you need to compare the result of summation with the original result by calculator, we have the first 6 decimal same. First 6 decimals are same. The error starts from the 7th decimal, which means that we have high accuracy. Okay, this is part A and part B. Part A, we find the Maclaurin series. Part B, we find the value of E. Part C, I need to find the Maclaurin series of the function x e to the power x. We already found this one. We already found this one. Okay. In part A, we already found this one. And now we need to find x multiplied by e to the power x. We need to find the Maclaurin series. How we can find the Maclaurin series? Should we calculate the function at 0 and the derivative at 0 and go for the original step, or we can use this one directly? And how? I have the function e to the power x. This is the Maclaurin series for the function e to the power x. We need to use this one to find x multiplied by e to the power x. How? Use e power of x. Yes, we will use e power of x, but how? Multiply by x. Yes, good, Farah. We have to multiply by x. Just multiply by x. X e to the power x is summation from n equals 0 to infinity. X, I will multiply x for x to the power n over n factorial. And this means it is equal to the summation from n equals 0 to infinity x to the power n plus 1 over n factorial. Just multiply, no need. You can go for the original step, yes, but it will take some time for you and it's difficult. More easy since you already find the function e to the power x, so you can easily multiply by x to find the function or the power series or Maclaurin series for the function x e to the power x. This is a Maclaurin series centered at 0. Okay, now we have another example. This is example number 3. This is example number 3. Should be number 3. Okay. We need to find the function, the Maclaurin series of the function f of x equal to sine x. F of x equal to sine x. F of x equal to sine x. So again, we will go for the same steps. My function f of x equal to sine x. Now, the derivative of f at x, first, sorry, calculate f0. Sine 0, which is sine 0, which is 0. Now, the derivative of sine is cosine x. So f prime of 0, which is cosine 0, which is 1, which is 1. Now, the second derivative of f of x. The derivative of cosine is minus sine x. So the second derivative at 0 is minus sine 0, which is 0. Still 0. Okay, the third derivative of x. What is the third derivative of the function? The third derivative. What is the derivative of minus sine x? Is it correct like that? Minus cosine x. Only Farah today respond with me. Where are the others? Are you sleeping? Okay, cosine 0 is minus 1. Minus 1. We can also calculate the fourth derivative if you want. So minus cosine x, the derivative of cosine is minus sine, and we have another minus, so sine x. So the fourth derivative at 0 is equal 0. So no need to continue because you will get same functions again. You will get same function again. Now we need to write sine x is equal to, by using Maclaurin theorem. Maclaurin theorem, f of 0 is it's 0. First term is 0. F of 0 is 0. F of 0, which is 0, plus f prime of 0, which is 1, times x, plus f double prime of 0, which is 0, x squared. 0 x squared over 2 factorial, plus Now the third one is minus 1 x cubed over 3 factorial, and so on. So sine of x is equal to 0. The first term is 0. First term is 0. So you have x, 0 times x squared, also 0. This one also 0. So minus x cubed over 3 factorial. The fourth term will be 0. The fifth term will be x to the power 5 over 5 factorial, and so on. So this is the series, or the Maclaurin series of sine x. This is the Maclaurin series of sine x. If you notice here, when we find the Maclaurin series for, for sine, it is equal to the summation from n equals 0 to infinity. It is alternating series. One positive term, one negative term, one positive term, one negative term. So it is alternating series. Minus 1 to the power n, x, 3, 5, 7, and so are odd. All the even parts are 0. So 2n plus 1, which is odd, over 2n plus 1 factorial. Plus 1 factorial. Okay, now we need to use this one. We need to use this Maclaurin series, sine of x, to find the integral of sine square, sine x square. To find the integral of sine x square, we have sine x from here is equal to x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial minus x to the power 7 over 7 factorial, and so on. So this is the Maclaurin series for sine x. I will use it to find the integration of sine x squared. I will use it to find sine x squared. So first we need to find the Maclaurin series for sine x squared. How we can find the Maclaurin series of sine x squared? How we can find the Maclaurin series of sine x squared? What do you think? Substitute x, yes, good, yes, substitute x by x squared. We will replace x by x squared. So each x will be replaced by x squared. Plus x squared to the power 5 over 5 factorial, and so on. Replace here each x by x squared. So the Maclaurin series of sine x squared is equal to x squared, x to the power 6 over 3 factorial, plus x to the power 10 over 5 factorial, maybe minus x. If you calculate another term, it will be minus x to the power 14 over 7 factorial. Okay, now we need to find the integration from 0 to 1 of sine x squared. We need to find the integration of sine x squared. So instead of going and integrate sine x squared directly, you need to integrate these terms only. You need to integrate these terms only. So these terms from 0 to 1, I have to integrate x squared minus x to the power 6 over 3 factorial plus x to the power 10 over 5 factorial minus x to the power 14 over 7 factorial, and so on. You have to integrate this one. You have to integrate this one. So The integration of x squared is x cubed over 3 minus the integration of x to the power 6 is x to the power 7 over 7 times 3 factorial plus x to the power 11 divided by 11 times 5 factorial plus here integration x14 will become x15 over 15 times 7 factorial and so on. So this will be from 0 to 1. You should substitute from 0 to 1. So now first I will substitute by 1 to find the integration. I will substitute by 1 first. So 1 over 3 minus x, substitute x by 1, so 7 times 3 factorial plus 1 over 11, 5 factorial plus 1 over 15, 7 factorial and so on. Minus, now we substitute by 0, but if you substitute by 0, all terms become 0. If you substitute by 0, first I substitute by 1. Now substitute by 0, so all the terms will be 0. All the terms will be 0. So you need to calculate these terms. You need to calculate these terms. Enough if you calculate the first fourth term is enough, because we need to find an approximation, actually not the exact, find an approximation of the integral, not the, but the result is accurate enough. It's accurate enough. So it is up to you, but first four term is enough. You need to add more terms, it's up to you. More terms mean more accurate results. If you find it is enough, the first four term is also okay, because we are finding an approximation. We are finding an approximation. So now we have the theorem. This theorem summarizes the power series or the Maclaurin series of some functions. The function e to the power x, as we just now evaluate, is equal to the power series x to the power n over n factorial, x to the power n over n factorial. Natural logarithm of 1 plus x, if you try to find the Maclaurin series of the natural logarithm 1 plus x, same, you will get it is equal to x minus x squared over 2 plus x cubed over 3 and so on. Sine x is equal to x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial and so on. So this is also you need to find the cosine. The cosine is same. Cosine is same. So this is are the Maclaurin series of this function. We already find the exponential e to the power x. We already find sine x. Now you can calculate cosine x and natural logarithm of 1 plus x, and you can prove these two functions. You can prove these two functions. So by this theorem, we end chapter 9. So if you have any question, please ask. Do you have any questions?